Welcome you all to this new lesson of circuit theory. Today we'll be discussing about maximum power transfer theorem in AC circuits. So you may remember in your first year classes, while you have studied basic electrical engineering, you studied about maximum power transfer theorem in DC circuits. So today we'll be discussing the same theorem, the same concept will be discussed for AC circuits. Unlike superposition theorem, Thevenin's theorem, Norton's theorem, unlike all those theorems, maximum power transfer theorem will not be applied to determine current through a particular branch or voltage across a particular branch. Rather, it will determine the value of load resistance or load impedance in a circuit for which maximum power will be transferred from source to load side. See, being engineer, our objective is to make the efficient circuits. Now, to have more efficiency, what we need to do, we need to produce more output for a particular input. Now, when output would be maximum, the condition for which output becomes maximum, output power becomes maximum, is discussed in maximum power transfer theorem. So today we'll be discussing about maximum power transfer theorem, its statement, explanation, and solve numericals. So what maximum power transfer theorem says? See, in an active network, maximum power is transferred to the load side when load impedance is equal to the complex conjugate of an equivalent impedance of a given network as viewed from the load terminals. What does that mean? See, suppose this is the voltage source. You all know any complex circuit can be represented by Thevenin's equivalent, where VTH is Thevenin voltage and ZTH is Thevenin equivalent impedance. Now, suppose a complex circuit is represented by this circuit. Now, this is the load impedance. You can vary load impedance. Now, vary load impedance, by varying load impedance, you will get some amount of power transferred from source to load side. Now, maximum power transfer theorem says for which load impedance maximum power will be delivered to the load side. So, maximum power transfer theorem says if the load impedance is complex conjugate of Thevenin's impedance or internal resistance of the network viewed from the load terminals, then only maximum power will be delivered to the load side. So maximum power transfer theorem says maximum power is transferred to the load side when load impedance ZL is equal to the complex conjugate of equivalent impedance of the given network, that is Thevenin impedance, as viewed from the load terminals. Okay. So what we need to do here, we need to go on varying load impedance, and this variation should be done until ZL becomes ZTH star. Now the question is, what is complex conjugate? See here, ZTH equals to ZTH is impedance, which is RTH plus JXTH, and ZL is load impedance RL plus JXL. Now, complex conjugate means the real part will be equal. But imaginary part will be imaginary part of load impedance will be minus of internal impedance of the network. That means if XTH equals to RTH plus JXTH, then ZL should be RTH minus JXTH. So, for example, this is J. For example, this is 4 plus J3, ZTH equals to. Then ZL should be equals to 4 minus J3. Okay. So what it implies? It implies the real part or resistance for both the cases should be same, but inductive reactance or capacitive reactance part or reactance part should be of opposite sign and equal in magnitude. So complex conjugate implies the the imaginary part should be equal and opposite in magnitude. So see here, if we go on adding these two ZL and ZTH, we will have no imaginary part. And if there is no imaginary part, then there will be no volt ampere reactive associated with the network, and hence maximum power will be delivered to the load. So what we need to do, we need to vary this load impedance, and we need to make RL equal to RTH, XL equals to minus XTH. For a given network, RTH and XTH are known. Being a design engineer, what your task is? Your task is to determine RTH and XTH first. Then you will put the load impedance, that is RL and XL value, equal to RTH and minus XTH. Okay. Now let us discuss how can we say that. Why RTH should be equal to RL, XTH should be equals to minus XL in order to get maximum power at the load side. That we are going to discuss now. So proof of maximum power transfer theorem. See, if this is the circuit and this is current I flowing through the circuit. So what can it say? I equals to VTH by ZTH by plus ZL, as these two are in series. These two are in series. Now ZTH is known, that is RTH plus ZTH. ZL is RL plus JXL. Now let us substitute the values. So I equals to VTH by RTH plus JXL plus RTH plus ZTH. So real part will be added and imaginary part will be added together. So finally we will get RTH plus RL plus J into XTH plus XL. Now what is the formula for load power delivered to the load? That is load power PL equals to I square RL. I current is flowing through load and RL is its load resistance. No power is consumed in reactance part, because over a full cycle power consumed by inductor or capacitor is zero, as we already discussed in AC circuits of basic electrical engineering. So I'm not going into details of that. You all know the formula for power across load is I square RL. Now let us substitute the value of I from this equation in this. So we'll get PL equals to this just by substituting the value of I from this equation. Now what is formula for maxima? Maximum power, formula for maximum power will be dP, derivative of power with respect to the variable. Let us differentiate it with respect to XL. We can vary RL or XL. So let us differentiate it with respect to XL and let us equate it to 0. This is the condition for maximum power, provided second order derivative is less than 0. So by differentiating PL with respect to XL, in this equation, we'll get this result. So this differentiation involves basic differentiation, which I'm not going to discuss here. So finally we'll get XL equals to minus XTH. So XL has to be minus XTH to get maximum power delivered to the load side. Now in the previous equation, let us substitute the value of XL. What was the previous equation? This was the previous equation. Here, if we substitute XL equals to minus XTH, this term will become 0. So PL will become VTH square RL by RTH plus RL whole square. So VTH square RL by RTH plus RL whole square. Now again, you can differentiate with this with respect to RL to get condition for RL, or you can do this simply like this. See, this equation can be written in this form. Why? Because after making simplification of this equation, you will get this one. This RT square plus RL square will be in the LCM. So RT square plus RL square plus 2 RTH RL. Here also RT square RL square will be cancelled. So in the numerator we will have 4 RTH RL. So RTH, 4 RTH, 4 RTH will be cancelled. So VTH square by RL, VTH square into RL by RTH plus RL square, which is this equation. So what we can do here, we can write this equation in this form. Now, how did we get this equation? This equation is obtained by putting XL equals to minus XTH. Now, when XL equals to minus XTH? XL equals to minus XTH when condition for maxima was satisfied. So this power should be maximum power. Now in this equation, in order to get maximum power, so this equation will be maximum when? If this term becomes 0, then only power will become maximum. Otherwise, whatever the value of this term, will never get maximum power, because if suppose this part is 0.1, so 1 minus 0.1 will be 0.9, so power will be 0.9 into VTH square by 4 RTH. Now if this value is 0, then power will be VTA square by 4 RTH into 1. So this term has to be 0 to get maximum power. So if this term is equated to 0, we'll get RTH equals to RL. So you can follow any procedure to prove this RTH equals to RL. You can differentiate it to get RTH equals to RL, or you can do it like this. Okay. So what we concluded here, we have got two equations. One is XTH equals to minus XL, and another is RTH equals to RL. So these two conditions has to be satisfied to transfer maximum power to the load side. So hence maximum power is transferred from to the load from source side if RL equals to RTH and XL equals to minus XTH for AC side. So this implies ZL has to be ZTH star. So this is the condition for maximum power transfer. Now, see, for this equation, if we put RTH equals to RL, if we put RTH equals to RL, then this equation will be let us substitute RTH by RL. So 2RL square is 4RL square. So 1 RL and this square term will be cancelled. So VTA square by 4RL. Now RTH equals to RL, so this can also be written as VTA square by 4 RTH. These equations are required to solve numerical. So VTA square by 4 RTH or VTA square by 4 RL is equation for maximum power transfer to the load side. Now efficiency at which maximum power occurs is 50%. So at 50% efficiency, this maximum power transfer can take place. Okay. Now let us discuss the steps which are involved to determine maximum power across a load or to determine the load impedance for which maximum power will be transferred to the load side. So first, first few steps are almost similar to Thevenin's theorem steps. So it would be more easier for you to understand as we already have gone through Thevenin's theorem. First step is identify and mark load terminals. Then remove the load as like Thevenin's theorem step. So first we have to identify and mark load terminals. Then we have to remove the load. While the load is removed, try to find VOC or VTH across the removed load terminals or open circuited load terminals. Third step is find ZTH. How to find ZTH, that we already discussed in Thevenin's theorem. Now this is step 4 and this is step 5. Now in step 4, here it comes the concept of maximum power. So what we discussed till now, in order to transfer maximum power, ZL should be equals to ZTH star. So once ZTH is found, ZL could be found by this equation. Okay. So if you are asked to determine the load impedance for which maximum power transfer will take place, first you need to find ZTH, then equate this equation, you'll get the load impedance for which maximum power will be delivered. And last step is find maximum power by using this formula. Okay. So these are the steps involved. Let us follow these steps to solve a numerical. Okay. Here it is given, this circuit is given. We are asked to find ZL. ZL is not given. So ZL is to be found by us to transfer maximum power to the load side, and also maximum power is to be found. See here, this is the ZL. So this is load terminals. These are load terminals. This is the entire circuit with which load is to be connected. Okay. So first step is identify the load. So load is simply identified as this is ZL, and we are asked to find value of ZL to transfer maximum power. So this is load, these are load terminals. So as for first step, identify and mark load terminals and remove the load. So we have removed the load here from A and B terminals. Clear? Now while load is removed, what you need to find? We need to find VTH as per step 2. So how to find VTH? It's very simple. VTH is voltage across this J6. Okay. Now what should be the flow of current? Current will be flowing like this. As this is open circuited, no current will be flowing through this path. Through this path, no current will be flowing. Okay. So current through this is 0 as it is open circuited. So entire current will be flowing through 4 and J6 ohm. So 4 and J6 ohm are in series, across which this 20 volt is applied. So voltage divider rule we can apply to find voltage drop across J6. Why voltage drop across J6 is to be found? Because voltage drop across J6 is equals to VTH. These are connected in parallel. So we'll find voltage drop across J6. So this will be, as per voltage divider rule, this will be 20 angle 0 multiplied by, this is the impedance across which voltage is to be determined. So this will be numerator. J6 will be written as 6 angle 90 degree. How can we write this? Just go through calculation of AC quantities, which we already discussed. There you could understand how J6 can be written as 6 angle 90 in polar form. So rectangular to polar conversion is need to be followed. Divided by 4 plus J6. So the equation will be, here it is written 20 angle 0 into J6 by 4 plus J6. Now J6 will be, as we are performing here division operation, so J6 will be converted to polar form. Similarly 4 plus J6 will be converted to polar form. Now once polar form is obtained, we can perform the division. 6 by 7.21 is 0.825. Angle 90 minus angle 56.3 is 33.70. So after multiplication, we'll get VTH equals to this. Now let us move to step 3. Let us find ZTH. To find ZTH, all the sources has to be deactivated. Voltage source has to be deactivated by a short circuit. So here we did it. ZTH is to be found looking back into the network from open circuited load terminals. So while looking back into the network, that means you are at point A, you are moving to point B. You can move through this path to reach at B, or you can move through this path to reach at B. So you have two alternative paths to reach at B. One is 4 ohm path, another is 6 ohm path. So 4 and 6 will be in parallel. So ZTH will be 4 parallel 6, that is 4 into J6 divided by 4 plus J6, which will give us this 4 into J6. J6 means 6 angle 90 and 4 plus J6 is this. So finally you'll get 3.33 angle 33.7. Now we have converted it into rectangular form so as to differentiate real part and imaginary part. So we know ZTH equals to RTH plus J XTH, which will give us RTH equals to 2.77 and XTH equals to 1.85. So as we know, as per step 4, to transfer maximum power to the load side from source, ZL should be equals to ZTH star. So ZL was what? ZTH was what? ZTH was 2.77 plus J 1.85. So ZL should be complex conjugate of this, that is 2.77 minus J 1.85. That is why 2.77 minus J 1.85. So this is ZL. So the impedance value ZL is found here as Z 2.77 minus J 1.85. That means when we'll get minus J if capacitor is placed. So if the equivalent impedance is R plus inductor, then equivalent load impedance will be R of same value and a capacitive reactance of same magnitude as like inductive reactance of the network. Okay, this is how you can find ZL or ZTH. Now RTH or RL is found. You can apply the formula written in step 5 to find maximum power delivered, that is VTH square by 4 RTH. So VTH is 16.5. Okay, and RTH will be 2.77. So this is the maximum power. So this is how we can calculate maximum, how much power is delivered to the load, how much maximum power could be delivered to the load side, and what is the condition for maximum power transfer. Based on that condition, how to determine the load impedance, all this we discussed. So let me summarize today's lecture. Today we have discussed about the maximum power transfer theorem statement. Why shall we study maximum power transfer theorem? What actually maximum power transfer theorem deals with? Proof of maximum power transfer theorem. The steps involved in determination of load impedance and maximum power for a particular circuit, electric network, and all those has been validated with the help of one example. So as of now, I'm ending up here today. In next class, we'll be moving towards Millman's and reciprocity theorem, another two theorems to determine current through or voltage across a branch, and reciprocity theorem is somehow different from these theorems. So we'll be discussing this in next class. Thank you all.